Question 16. Electrons are emitted from a metal surface when a certain frequencies of electromagnetic radiation are incident on the metal surface. The graph below shows how the maximum kinetic energy, EK, of the emitted electrons varies with the frequency F of the incident radiation. So we take a look at the graph. This is the maximum kinetic energy up here. This is the frequency of the light shown onto the metal, and you can see above a frequency of 4.4 times 10 to the power 14 Hz, you're going to get photo electrons emitted with excess energy, which is going to appear as kinetic energy. But below that 4.4 times 10 to the power 14 Hz, you're going to get no photo electrons emitted. It's this point here where you get when you have a shiny frequency of 4.4 times 10 to the power 14 Hz. This is the threshold frequency, and that's the frequency of a photon which will emit a photoelectron but with no kinetic energy. So this is the this is the metal's threshold frequency. So if we put that down over here, we can say the threshold frequency, we'll call F0, is going to equal to 4.4 times 10 to the power 14 Hz. That's the threshold frequency. So to find the work function is just simply HF0, where H is Planck's constant. So therefore the work function is now going to be 6.63 times 10 to the minus 34 multiplied by the threshold frequency. You're finding really the energy of the photon, which is going to eject an electron with no kinetic energy. So we'll multiply that by that threshold frequency, 4.4 times 10 to the power 14. And if we do that in a calculator, we end up with a value of 2.9 times 10 to the power minus 19 joules. That's the energy of that photon, which will emit a photoelectron from the metal surface but with no kinetic energy. And we're looking for the following answer: 2.9 times 10 to the minus 19. The answer is B. Question 17. Two loudspeakers LS1 and LS2 produce coherent waves. A microphone connected to an oscilloscope is used to detect the sound from the loudspeakers. So you can see the situation here. You've got two loudspeakers. That's the central line heading towards P. You've got your microphone. You move up and down, and you should hear maxima and minima. The path difference for the sound at detected position P is 0, because that's the central maximum. And it tells you that the path difference for the sound detected at position Q is 1 wavelength. So if you're 1 wavelength away, that's the first maximum sound that you hear. Now if we do a diagram here of all the maximums and minimums, you can see if I represent the maximum sound with a open circle and a minimum sound with a black circle, you can see the following more clearly. You have the central maximum loud sound, because the path difference there is 0. 1 wavelength later, you're going to have position Q. You're going to hear the first maximum sound. So we should hear the following. We stand at P and we hear the loud sound, we hear a quiet sound and then a loud sound. So that's what we're looking for in the responses. So let's see what we can find then. The amplitude remains constant is not a answer, so we can rule that one out. The amplitude is a minimum at P and increases to maximum at Q. No, the central maximum is a maximum one. All the sound waves are either in phase, so that one is wrong. The amplitude is a maximum at P and decreases to a minimum at Q. No, because in between you're going to hear a minimum sound, so we can rule that one out as well. Response D, the amplitude is a minimum at P, which is wrong because it's a maximum at P, so we can rule that one out. Oh, we'll get the last one here. The amplitude is a maximum at P. Well, that's correct. It's a maximum at P. Decreases to a minimum, correct. And then increases to a maximum at Q, the first maximum there. So our answer to this one is going to be E. Question 18. Light from a gas discharge lamp is used to produce the line emission spectrum drawn as shown X, Y and Z, and that's the increasing wavelength this way. The spectral line at position Z is brighter than the spectral lines at position X and Y. And the reason for that is we can just know right away that if it's a brighter spectral line, we know that more electrons are making that particular transition to give out that line there. Because a brighter line, the more photons. So we're looking for more electrons per second to make that transition, and that looks like it's going to be this one here. C, more electrons per second make the transition between energy levels that produce line Z, and that is correct, because the more photons that are released, the more electrons that make that transition, more photons are released, the brighter the line. Question 19. A ray of monochromatic light passes from air into a semicircular glass block as shown. I'm asked to find which row in the table gives the critical angle and the refractive index for the light in the glass. Well, we know that the angle which the ray of light makes inside the glass, between the ray of light and the normal, that produces a ray of light leaving at 90 degrees to the normal, which means running across the edge of the glass. That angle is the critical angle. So right away we can say that the critical angle, theta c, has got to be equal to 39 degrees. Now we know that the formula for the critical angle, sine theta c, is equal to 1 over the refractive index. We can get that from the relationship sheet. So we can just do a wee bit rearranging and get the refractive index is 1 divided by sine of theta critical. Just plug in the numbers. 1 divided by sine of 39 degrees, and we do that in our calculator. We end up with a refractive index equal to 1.58. So we're looking for 39 degrees and 1.58. So 39 degrees here, and we have got no 1.58, but if we go to two significant figures, it'll be 1.6. So our answer is A. Question 20 is the AC question, AC electricity one. The output from an AC power supply is connected to an oscilloscope, and the trace on the oscilloscope screen is as shown. The Y gain settings are told 1.5 volts per division, and the time base setting on the oscilloscope is 2.5 milliseconds per division. I'm being asked to find which row in the table shows the RMS voltage and the frequency of the supply. Well, we know right away that the RMS voltage is going to be equal to the peak voltage divided by root 2. So VRMS is the peak voltage divided by the square root of 2. So what is the peak voltage in this case? Well, if we go and look very closely, we can see we have the centre line here. We have 3 boxes, and we know that each box stands for 1.5 volts, or one division stands for 1.5 volts. We've got 3 of them, and therefore we can do the following calculation. The peak voltage is going to be 3 boxes times 1.5 divided by square root of 2. And if you do that in your calculator, you end up with a value of 3.2 volts VRMS. Now, how do we calculate the frequency of the supply? Well, we do the same thing. We identify one complete cycle. That's from there. If we do one complete cycle, it's from starting here all the way up, all the way down to the turns. One complete cycle covers 1, 2, 3, 4 boxes. So we can do the following. We can do the period of the wave. Period T is going to be 4 boxes multiplied by what one box stands for. In this case, it's 2.5 milliseconds. 2.5 times 10 to the power minus 3 seconds, and we work out that we get a value of the following. 4 times 2.5 of that, we get a period T. I'll put in fraction to be 1 over 100, and therefore we can just do the following next formula, that the frequency is always related to 1 upon the period T, and it's going to be 1 over 100, which is going to give you 100 Hertz. So we're looking for the following. We're looking for a frequency of 100 Hertz and a VRMS of 3.2 volts. 100, it's got to be this one here. It's got to be answer B.